Hi folks, this video is a second part. It's a part two to yesterday's video, which had to do with this question here. Okay, it had to do with ocean tides. Okay, that's a situation where it's a periodic function, something that can be modeled by a sine curve or a cosine curve or a sinusoidal curve if you want to use that word. Okay, today's question is kind of a fun one because we're talking about Ferris wheels. Um, Ferris wheels are those huge wheels that turn around in circles and they get very scary when you're very high up. For example, this one is ridiculously big. It's 40 meters. That's the diameter of the circle. So as you know, Ferris wheels have riders on them. Well, that's not a very good drawing. And remember, a diameter of a circle is all the way through the center, all the way across. It's 40 meters. And that means it's 20 above and 20 below. And this wheel, this Ferris wheel, it rotates around the circle. It takes 30 seconds to rotate around. Okay, so what we're going to do today is we're going to graph this. We're going to come up with a graph or a sketch, and then we're going to come up with an equation at the end. It says right there, use the equation to answer some questions about that. So I'll erase this here. And let's start with our drawing. It says draw a graph to show a rider's height for 2 revolutions of the wheel, starting at the lowest position. Okay, so let's draw this. Now the reason why I don't start it off by doing this and saying, here's our curve, is because a Ferris wheel, one important thing about a Ferris wheel is that you don't want it to go below the ground. Otherwise, you're going to hurt the people on the Ferris wheel. Okay? So this is a height right here. We'll call this the height. And I didn't really label yesterday's graph very well. So that's not very good on my part. This part here will be the height. I believe it's in meters. And along the x-axis, as usual, we're going to put the time. And it's the rotation time, so it's going to be in seconds. Okay, and we know two things. We know that the circle has a diameter of 40 and has its center 21 meters above the ground. So I'm going to start by putting 21 as our closest center here. 21 meters above the ground. The diameter is 40, which means the radius of that circle is 20. So it goes 20 down and 20 up. 20 down, 20 up. So 20 down from 21 would bring us to 1 meter off the ground. And that's where people would be at their lowest point. And the highest point would be 20 above 21. So 21 plus 20, it'd be 41. That's the highest point right there, 41 meters. That is very high off the ground. If any of you have dove off a 10-meter diving board, that's pretty high, isn't it? Can you imagine 41 meters? At this point, if I wanted to waste your time, I'd Google what the average Ferris wheel is, and just to see if this makes sense whatsoever. Because sometimes in math, they'll give you a word problem that has no sense being in reality because it's just too crazy. But this may actually be a true situation. I'm not sure. I just took it from some math book somewhere. Okay, so draw a graph to show a rider's height for 2 revolutions of the wheel. Okay, it takes 30 seconds for it to rotate once. And it says we're going to start here at the lowest position. We're going to be starting down here. So we're going to start down here. And it's every 30 seconds, we will be back to the lowest position again. Okay? And we're doing 2 revolutions. So let's say there's 30 seconds. And then let's say this is 60 seconds so that we can do 2 revolutions of the wheel. So that will be right there, and that will be right there. Those are our 2 lowest points, both at 1 meter high. And the upper part, well, the nice thing about these kind of graphs is you can go between 30 and 0. This would be 0 seconds at the very beginning. Halfway is 15 seconds. And halfway between 30 and 60 is 45. If you wanted to, you could just add 30 plus 60, divide by 2, you get 45. And those will be our 2 spots where we're going to be at our highest point. Okay, and this is a sketch. It doesn't have to be perfect, but it still should be as nice as we can make it. Notice my multicolored pen here, just to make it look nice for you and for me. There we go. So we've just sketched 2 revolutions of this wheel. Okay, that wasn't so bad, was it? Now the next one says write an equation that would match this graph. Use sine or cosine. Which one is easier? Maybe we'll do both, but I'm going to start with the one that is easiest. Okay, if you remember, I'm going to start by going like this, y equals. If you remember from the last lesson, cosine is a graph that on the y-axis, it starts at either an extreme top or extreme bottom. Cosine starts from the extreme bottom if we have a negative sign in front. Okay, so we're going to have a negative, and it's going to be cosine because it's starting at the extreme bottom. If this curve had started somewhere in the middle here, like here, then we would have went with sine, that being easier. Okay, but cosine is easier in this case because it starts at the extreme, and in this case extreme bottom, so we put the negative sign to flip it. I hope I haven't said that too many times. I don't want to bore you. Now the next thing after this negative sign is the amplitude. The amplitude is the distance between the axis of the curve, sorry it's not very straight, from here to here, the axis of the curve to the top, or you could say the axis of the curve to the bottom. We already know that this distance is, go ahead and say it, that's right, it's 20. Okay, then we're going to write cos. Does this thing shift left or right? Does it have a horizontal shift if we're starting right here? It does not, because this is the typical place that cosine starts, either at the very bottom or the very top. If we were looking at this spot here, if we were looking here, we'd say, yes, cosine has moved to the right 15. It'd be 15 seconds. It had moved to the right 15 seconds. Then we would put things in brackets and whatnot. But I'm going to leave a little space there. And just write the x there. Actually, I don't even need brackets. I don't even need brackets because it isn't moving left or right at all when we're talking about this point right here, which we're going to talk about here. Now the other thing is, remember the period goes right here. The period is the number that goes here, but it's not really the period. Here's the formula. It's actually the value that we say is k. And here's the formula. Yesterday's lesson already talked about this formula. We don't know what k is. We have to figure out what k is to put it into this equation here, okay? So we'll use this formula here. Period is equal to 360 divided by k. So really k, if we want to know what k is, if we were to use cross multiplication, really all we're doing is we're taking 360 dividing by the period, and that will give us k. Okay. So we're going to take 360 and divide by what we see is the period. Well, what's the period here? Guess what? It even tells us right here in the question. The period is every 30 seconds. Okay, it's every 30 seconds. So 30 is our period. So we're going to 360 divided by 30. Oh wow, we didn't really need a calculator for this. K is going to be 12. Okay, so I put the 12 right there. There's no shift left or right once again, so I'm not putting this in brackets. I'm not putting a bracket around the x and putting a plus or a minus here. But on the end, it's going to be a plus or a minus depending on what the axis of the curve is. The axis of the curve is this yellow line. It is 21. And that is our equation. Okay? So we could go and punch this into Desmos and graph it, and we would get a graph that looks a lot like this. Use the equation, however, not the graph. Use the equation to answer how high the rider would be after 6 minutes. This is where I messed up when I first looked at this question. I just put a 6 where I see the x, because I know x, the x-axis here is referring to time, and I threw the 6 in where the x is. Not a good idea. Can you see the mistake I made? The mistake I made is right here in green. Careful. 6 minutes is really 120 seconds. So I'm going to use my calculator and I'm going to put 120 seconds or 120 where the x is, because this curve here is assuming that we're talking about seconds, and that's why the 12 there also assumes that we're talking about seconds. So we needed to use seconds here. So you take a calculator and you can start with I don't know, 12 times 120. There's different ways to do it, but I'm just going to go 12 times 120. Take the cosine of that. Make sure your calculator's in degree mode. Wow, you get 1. Interesting. Multiply that. Multiply 1 by negative 20. Well, that's just going to give us negative 20. Negative 20 plus 21 is 1. So you get 1 meter high. Does that make sense at 120 seconds? Actually, it does, because 1 revolution is 30 seconds, 60 seconds, 90 seconds, 120 seconds. We should be at 1 meter high at 120 seconds. So this equation, we know we've done it right. Okay? Now, we could stop there. We could say thank you very much, folks, and the video is over. But just for fun, let's just try. What if your teacher was picky and said, can you do an equation that uses sine? Okay, and if your teacher asked you to do that, then you'd say, okay, sine. You'd go back here and you'd look. Sine starts in the middle, somewhere along this curve. And so I'm going to pick this spot right here. Yes, you could pick this spot or this spot or this spot, but I'm going to pick the one closest to this y-axis here. And I'm going to ask myself right now, how far over is it from here to here? Well, a good guess would be that it's just between 0 and 15. So that'd be about 7.5 seconds, okay, to get to this spot right here. It's between the 0 and the 15, which is about 7.5. And then what we do is write it down the same, except for in this case, sine moves upwards from the middle, right? So if we're starting from here and we're moving upwards, then we don't need sine to be negative. If we had started from here, then we'd need sine to be negative because we're moving downhill. Okay, sine starts uphill naturally. So let's just remember, sine is going to be positive. The amplitude is still 20, just like the question above. It's still going 20 up and 20 down. Okay, the k value is still the same. We don't need to redo that. But this time we're going to have brackets because sine has moved over to the right 7.5 seconds. Now remember, when you do the brackets, it's always the opposite of what you think. Instead of a plus 7.5, you put a minus 7.5. Those brackets always lie to us. And then on the end, the median of the curve, or the middle of the curve, or the axis of the curve is 21. So just for fun, just to make sure this equation actually works, let's see if we get the exact same answer as of 1 if we were to type 120 seconds right where the x is here. And if I'm wrong, it's going to be very embarrassing because I will have done this video and wasted your time. So hopefully the level of tension is brought up right now, and we're very excited, just like a magician doing a magic trick. I don't have a drum roll or anything. But let me get to what I'm doing. I'm taking 120, plugging it in where I see the x, and going 120 minus 7.5. I hit equals, 112.5. I'm going to multiply that number by 12 times 12. 1350. Now I want the sine of 1350. Negative 1. Very interesting. Negative 1 times 20 is negative 20. Negative 20 plus 21 is 1. We got the exact same answer when we did this equation as when we did this equation, when we plugged in 120 seconds into each equation. It makes me feel very confident that this is also correct. This one is correct, and so is this one. Okay? So if your teacher decides to ask you for you to write this using sine, an equation using sine, you've now seen what the heck they're talking about. Having said all of that, this video is a little shorter than the first part because I didn't have to give all that preamble, and I hope that you kind of get what I'm talking about here. Wow, look at all that crazy writing. I hope you made sense of it. Have a great day.